Europa is not what you think. This is not just a ball of ice drifting around Jupiter. Europa is an ocean world. And, as if that wasn't strange enough, that ocean might contain the basic ingredients for life. Beneath that frozen shell lies one of the most important unanswered questions in all of science. So, let's go inside. This is one of the first detailed images of Europa ever captured. It was taken by NASA's Galileo spacecraft in the late 90s, and when scientists looked at it closely, something didn't add up. The surface was too smooth, too young. There were almost no impact craters on a moon that should have been battered by billions of years of collisions. Instead, the entire surface was covered in long, reddish-brown streaks, fractures stretching for hundreds of kilometers, like veins on the back of a hand, as if something beneath was pushing outward. Now, the problem with these early observations is that beyond looking fascinating, they didn't tell us what was actually going on beneath the ice. They only raised more questions. What is under there? And why does this moon look like it's alive? On November 23, 2022, the JWST turned its instruments toward Europa. Using the integral field unit of its near-infrared spectrograph, an instrument mode that provides spectra on the surface, two independent research teams analyzed the same dataset and made the same discovery: carbon dioxide on Europa's surface. Now, carbon dioxide had been detected on Europa before. That was not new. What was new was where they found it concentrated and what that location implied about where it came from. The CO2 was most abundant in a region called Tara Regio, a geologically young area of disrupted terrain known as chaos terrain. These are places where the surface ice has been broken apart, shifted, and refrozen, as though something from below pushed through and rearranged the landscape. Previous observations from the Hubble Space Telescope had already shown evidence of ocean-derived salt in Tara Regio. Now, Webb was showing that carbon dioxide was heavily concentrated there as well. Webb's spectrograph detected absorption features around 4.25 and 4.27 micrometers in wavelength. The 4.27 micrometer feature corresponded to pure CO2 ice. The 4.25 micrometer feature corresponded to a trapped form of CO2, and its spectral signature closely matched that of CO2 trapped onto oceanic salt. That detail is critical. It links the carbon directly to the salty water beneath the ice. As Samantha Trumbo, the lead author of one of the two papers, explained, the carbon probably has its ultimate origin in the internal ocean. And the second team, led by Geronimo Villanueva of NASA, reached the same conclusion. They also measured the carbon, 1:2 to carbon, 1:3 isotope ratio, and found that it pointed toward an internal source rather than delivery by meteorites or other external impacts. On Earth, life likes chemical diversity. Carbon is the backbone of every living molecule. Understanding the chemistry of Europa's ocean, as Villanueva put it, will help us determine whether it is hostile to life as we know it, or whether it might be a good place for life. But here is the strange part. Scientists have long debated how much Europa's ocean connects to its surface, and that question has been one of the biggest drivers of Europa exploration. This discovery suggests that even before we drill through the ice, we may already be looking at clues about what the ocean contains. And this was not an elaborate, months-long observation campaign. As Heidi Hamel, an interdisciplinary scientist on the Webb team, noted, these observations only took a few minutes of the observatory's time. Even with that short period, they were able to do really big science. It was a first hint of all the amazing solar system science Webb could deliver. Now, finding carbon dioxide on the surface was a breakthrough. But it also raised a difficult question. If the CO2 was being supplied from below, and if it is unstable on the surface, then how does it stay concentrated around the equator? Europa's surface temperatures range from about 30 Kelvin at the poles to roughly 100 Kelvin at the equator. Carbon dioxide ice at those equatorial temperatures would sublimate. It would turn directly from ice into gas and begin hopping across the surface in a process called ballistic transport. Each time a CO2 molecule sublimated, it would fly a short distance, land, stick to the surface for a while, then sublimate again. Europa's atmosphere is so thin, about 10 million times less pressure than Earth's oxygen atmosphere, that sublimation would happen almost immediately. In 2025, a team published the results of Monte Carlo simulations modeling exactly this process. They tracked 10 million virtual CO2 particles released from a hypothetical source at the center of Tara Regio and watched how they moved across the surface, bounced, settled, and eventually were destroyed by photoionization. What they found was striking. At equatorial temperatures, the average transport angle for a single sublimation event was only about 1 degree, meaning each hop carried a molecule roughly 30 kilometers. The flight time for each hop averaged about 100 seconds. But the residence time, the time a molecule sat on the surface between hops, varied enormously with latitude. Near the equator, it was less than a second. At the poles, where the surface temperature drops to 30 Kelvin, it exceeded 1 billion years. The molecules would essentially freeze in place and never move again. The result was that CO2, released at the equator, would migrate toward the poles over a timescale of roughly 10 days. Within about 100 days, the vast majority of the molecules had settled at high latitudes, forming a ring around each pole. Under steady-state conditions, meaning if CO2 had been supplied continuously for many years, the model predicted that almost all of the CO2 should accumulate near the poles, not the equator. But that is not what Webb observed. Webb saw CO2 concentrated at the equator, around the chaos terrains. Tara Regio, Powys Regio, both near the equator, both enriched in carbon dioxide. So, what does that mean? The researchers proposed 2 possibilities. The first is that some process is destroying CO2 far faster than ultraviolet photoionization alone can account for. The estimated lifetime of CO2 due to solar UV photoionization is about 4 years. But Jupiter's magnetosphere also bombards Europa with high-energy electrons and ions, and recent data from the Juno mission suggests that these particles dissociate water ice on the surface at a rate several orders of magnitude higher than solar UV alone. If the same applies to CO2, it could be destroyed over 100 times faster than the photoionization rate, breaking apart in a matter of days rather than years. If that were the case, CO2 molecules would be destroyed before they ever had a chance to reach the poles, and the equatorial concentration would make perfect sense. Moreover, recent magnetohydrodynamic simulations have revealed that irradiation by ions and electrons is significantly higher at high latitudes compared to low latitudes, due to how Jupiter's magnetosphere interacts with Europa. That means CO2 that does manage to drift poleward would be destroyed even faster once it got there. This latitudinal dependence aligns neatly with what Webb observed. The second possibility is that something on the surface is trapping CO2 in place for much longer than the models assumed. Surface roughness pits, cracks, bladed terrain formed by ice sublimation could increase the effective residence time by forcing a molecule through many sublimation cycles before it escapes a pit. But the simulations showed that roughness alone would only increase the time by a factor of about 10. And the observations required something more like a factor of 1,000,000. The team concluded that the rapid destruction scenario was more likely, and if that is the case, it means the CO2 we see on the surface has a lifetime measured in tens of days, which means it must be actively supplied. Something beneath the ice is pushing carbon to the surface right now, not millions of years ago, not thousands, right now. While the Webb telescope was revealing what was coming up from below, another mission was measuring what was happening on the surface itself. On September 29, 2022, NASA's Juno spacecraft flew within 220 miles of Europa, about 354 kilometers, at a speed of 23.6 kilometers per second relative to the Moon. It was the closest any spacecraft had come to Europa since the Galileo mission. And Juno carried something Galileo did not: a time-of-flight ion mass spectrometer called JADE, the Jovian Auroral Distributions Experiment. This instrument can measure the energy, direction, and composition of charged particles with a precision that Galileo's instruments could not match. And it provided the first direct sampling of Europa's atmospheric composition. Europa's location within Jupiter's radiation belts means that charged particles from the giant planet are constantly bombarding the icy surface. When those ionized particles strike water ice, they split the molecules apart, breaking them into hydrogen and oxygen. The hydrogen, being light, escapes relatively easily into space. The oxygen, being heavier, tends to stick around, either forming a thin atmosphere or getting embedded back into the surface ice. In a way, the entire ice shell is being continuously eroded by waves of charged particles washing up upon it. Scientists had long understood this process in theory, but the actual numbers had never been directly measured. Previous model-driven estimates for the rate of oxygen production ranged from about 5 kilograms per second to over 1,100 kilograms per second. That is an enormous range spanning more than 2 orders of magnitude. And the answer matters because some of that oxygen might eventually work its way down through the ice and into the subsurface ocean, where it could serve as a source of metabolic energy for life. Juno settled the question. As it flew through Europa's space environment, JADE identified and measured hydrogen and oxygen ions that had been created by the charged particle bombardment and then picked up by Jupiter's magnetic field. The instrument confirmed that molecular hydrogen and molecular oxygen are the primary atmospheric constituents consistent with what remote observations had suggested, but verified for the first time by direct in situ measurement. The result was surprising. Europa produces about 12 kilograms of oxygen per second. That is roughly 1,000 tons every 24 hours. Enough to keep 1 million humans breathing for a day. It sounds impressive until you realize it is at the very low end of all previous estimates. Juno's data also revealed something else that nobody anticipated. The hydrogen atmosphere around Europa was dominated by a non-thermal, escaping population. In simpler terms, the hydrogen molecules leaving the surface were moving faster than you would expect from surface temperature alone. Something was giving them extra energy, possibly atmospheric sputtering, direct surface sputtering, or Joule heating, caused by the interaction between Europa's atmosphere and Jupiter's magnetosphere. Before this flyby, the prevailing understanding was that hydrogen left the surface with a speed distribution matching the local temperature. That turned out not to be the case. And here is why the lower oxygen number matters for the question of life. If less oxygen is being produced on the surface, then less oxygen is available to seep into the ocean. Previous estimates of oxygen delivery to the ocean ranged from less than 1 kilogram per second to as high as 300 kilograms per second. With the new Juno data, the total amount of oxygen that could be retained in the surface ice is constrained to less than 18 kilograms per second. The energy budget for any potential biology in that ocean is tighter than we thought. Juno also measured the rate at which the surface itself is being eroded by this process. The radiolysis-driven dissociation of surface ice requires about 13 kilograms per second of water ice to be broken apart. That translates to a surface erosion rate of about 1.5 centimeters per million years, which is slow, but is actually more significant than erosion from meteoroid bombardment, making radiolysis the dominant way Europa's surface is being worn away. This does not rule out life. It simply means the window is narrower, and it remains to be seen whether the rate Juno recorded on that single day in September 2022 is typical, or whether plume activity, orbital position, and upstream conditions cause it to fluctuate over time. Now, among Europa scientists, there has been a long-running argument. Two camps, the thick ices and the thin ices. Pretty much everyone agrees that Europa has a subsurface ocean. The argument is about the ice shell above it. How thick is it? And does liquid water ever get close to the surface? The thin ices pointed to Europa's chaos terrain, those regions where the surface looks like icebergs that have broken apart, drifted, and refrozen in place. It looks remarkably like sea ice on Earth. Their argument was straightforward. The ocean must come very close to the surface, sometimes even melting through, to create a landscape like that. The thick ices disagreed. They argued that physics makes a melt-through scenario essentially impossible. Europa's surface is directly exposed to space. Space is cold, very cold. So cold that at Europa's distance from the Sun, ice behaves thermodynamically like rock does on Earth. You would never see hundreds of square kilometers of rock suddenly liquefying into lava at the surface. That is essentially what the thin ices were proposing, just with ice instead of rock. Over the decade, after the Galileo mission ended, the thick ices' mathematically rigorous arguments carried the day. But they still had a problem. They could not explain how chaos terrain actually forms. Then, in 2011, a paper published in Nature offered a solution that satisfied both sides. Brittany Schmidt, a young geophysicist at the University of Texas at Austin, along with Don Blankenship, Wes Patterson, and Paul Schenck, proposed something elegant. A way to have thick ice and liquid water near the surface at the same time. A bit of thin ice on top of a lot of thick ice. Their model works like this. Deep inside Europa's ice shell, a plume of warm ice, not liquid water, but warm, solid ice, similar to the rocky mantle plumes inside Earth, rises upward. As it pushes the ice above it higher, it reduces the pressure on the ice at intermediate depth. That change in pressure causes ice at a few kilometers below the surface to partially melt. A lens of liquid water forms a lake trapped inside the ice shell, with the ocean still far below. Liquid water is slightly denser than frozen ice. So as the ice melts, it takes up less volume, and the surface above sinks downward. The thicker crust at the edges creates higher pressure than the thinner crust at the center, so the water flows inward, forming a lens shape thickest in the middle, thinnest at the edges. The melting water is pinned in a confined area above the rising plume. As the lid over this lake sinks and bends, cracks open from below. Briny water under pressure squirts into those cracks and percolates into the porous, granular ice above. The crust never actually melts through, but it becomes saturated with water. Large chunks carve off, narrow blocks tilt sideways. The surface disrupts into chaos. And when the geologic activity eventually subsides and the lake begins to refreeze, the water saturating the crust expands as it solidifies, and the disrupted terrain domes upward. That explains what we see at places like Connemara chaos terrain that stands higher than the surrounding ice, with matrix material domed up between tilted blocks. At Tara Regio, by contrast, the surface is sunken below the surrounding terrain. Schmidt and her co-authors argued that this means we might actually be looking at chaos in the middle of forming a lake that was still liquid at the time Galileo observed it. They estimated that a melt lens of 20,000 to 60,000 cubic kilometers of liquid water probably lies beneath Tara Regio. That is at least the combined volume of North America's Great Lakes, just a few kilometers below the surface. And the dark stains associated with chaos terrain could well be the salts and other materials dissolved in that lake water. Land at Tara, and you might be able to taste Europa's ocean. For context, the other prime candidate for subsurface life in our solar system is Saturn's moon Enceladus, where the Cassini-Huygens mission discovered plumes of water erupting from a subsurface salty ocean also in contact with rock at the seafloor. But Europa's ocean is far larger, and the evidence for chemical exchange between its interior and surface is now mounting in ways we have never seen before. New observations from the James Webb Space Telescope are now painting an even richer picture. For decades, scientists pictured Europa's frozen surface as a still, silent shell. A study led by Richard Cartwright used Webb's near-infrared spectrograph to examine two regions in Europa's southern hemisphere, Tara Regio and Pauis Regio. What they found challenges the assumption that Europa's surface is static. The team detected crystalline ice, both at the surface and at depth, in these chaos regions. That was unexpected. Under Europa's intense radiation, ice should become amorphous, disordered, with its crystal structure broken apart by constant bombardment. The fact that crystalline ice was present meant that the ice was actively recrystallizing. And for ice to recrystallize, it needs warmth. The surface, they concluded, is porous enough and warm enough in some areas to allow this process to happen. The team's laboratory experiments played a crucial role. They studied how water freezes under Europa-like conditions, where the surface is constantly hit by charged particles from space. Unlike on Earth, where ice naturally forms a hexagonal crystal structure, the intense radiation on Europa disrupts that structure, turning it into amorphous ice, a disordered, non-crystalline form. By studying how ice transforms between these states, scientists can learn about the Moon's surface dynamics and how quickly the ice is being reworked. They also detected higher levels of carbon dioxide in these regions than in the surrounding terrain, confirming the earlier Webb findings. And they found carbon-13, an isotope whose presence is difficult to explain by any mechanism other than an internal origin. As Cartwright noted, every road leads back to the interior. The team also found strong evidence for sodium chloride in Tara Regio table salt, probably originating from the interior ocean, along with some of the strongest evidence for hydrogen peroxide on Europa. As Cartwright described it, the chemistry in this location is really strange and exciting. Ujjwal Raut of the Southwest Research Institute said the data showed strong indications that what they were seeing must be sourced from the interior, perhaps from a subsurface ocean nearly 20 miles beneath Europa's thick, icy shell. So the picture is this: Europa is not a static world. Its surface is being actively modified from below. Material from the ocean is reaching the surface through chaos terrains. The ice is warm enough in places to recrystallize. Carbon, salt, and other compounds are being cycled from the deep interior to the surface on geologically recent timescales. It is a dynamic world, and it is far from frozen in time. To get real answers, we need a dedicated mission, and that mission is already on its way. Europa Clipper launched on October 14, 2024, on a SpaceX Falcon Heavy rocket from Kennedy Space Center. The launch had originally been planned for October 10, the opening of a 2-1-day launch window, but was delayed by Hurricane Milton, which swept through Florida just days before. NASA had a well-defined hurricane response plan. A ride-out team was deployed at Kennedy Space Center to keep essential infrastructure running while the storm passed. After it cleared, the team assessed the damage, confirmed the spacecraft was safe, and reset the launch for 4 days later. It lifted off at 16:06 UTC. The spacecraft is now on a Mars-Earth gravity assist trajectory. It flew past Mars on March 1, 2025, at an altitude of 884 kilometers, picking up a gravitational boost. The Mars flyby also provided an opportunity to calibrate two of the spacecraft's instruments, the thermal imager and the ice-penetrating radar. From Mars, Europa Clipper is heading toward an Earth flyby in December 2026. After that, it swings out toward Jupiter, arriving in April 2030. Once at Jupiter, Europa Clipper will not orbit Europa directly. The radiation environment is too harsh. Instead, it will orbit Jupiter on a highly elliptical path, performing 49 close flybys of Europa over approximately 4 years. Each flyby will dip the spacecraft into the radiation zone just long enough to collect a massive volume of data, then pull it back out to safer space where it can downlink information, recharge its batteries, and prepare for the next pass. All 9 science instruments are designed to operate simultaneously during each flyby. The instrument suite is comprehensive: an ultraviolet spectrograph to study Europa's atmosphere and search for plumes, wide-angle and narrow-angle cameras for detailed surface imaging, an infrared spectrometer to map surface composition, a thermal imager to detect warm spots, an ice-penetrating radar operating at 2 frequencies to probe the structure of the ice shell and search for subsurface water, a mass spectrometer and a surface dust analyzer to identify the chemical makeup of particles ejected from the surface, a magnetometer and a plasma instrument for magnetic sounding of the ocean, and a gravity and radio science investigation that uses the spacecraft's own communications system to measure Europa's gravitational field. During its cruise to Jupiter, Europa Clipper has already demonstrated its versatility. In November 2025, the spacecraft's ultraviolet spectrograph was repurposed to observe the interstellar Comet 3, I, Atlas. At the time, the comet was hidden from Earth-based observatories by the Sun's position. Europa Clipper was positioned at about 1 astronomical unit from the comet and detected hydrogen, oxygen, and dust features in its coma, the cloud of gas and dust surrounding the nucleus. The mission bridged a critical gap between Mars-based observations and later Earth-based data, confirming that water ice was sublimating from the comet and that its activity appeared stable. As of early 2026, all spacecraft systems are healthy. Navigation performance has been excellent, all executed maneuvers have been within tight tolerances, and 3 of the 7 planned trajectory correction opportunities between launch and the Mars flyby were cancelled because they simply were not needed. The downlink is performing about 3 decibels better than pre-launch predictions. The spacecraft has passed its first solar conjunction, commissioned its Ka-band communications, and completed self-compatibility testing for electromagnetic interference. Europa Clipper is on track. The spacecraft also carries a small device called the Canary Box, an assembly of electronic components mounted to the spacecraft's vault that serves as an early warning system. It monitors the health of certain transistor components in real time, and during the Jupiter tour, it could alert the team if radiation damage threatens critical systems. It is a small detail, but it reflects the level of care built into a mission designed to survive one of the harshest environments in the solar system. So here is what we know so far. Europa has a salty ocean of liquid water beneath its ice shell, probably in contact with a rocky seafloor. That ocean contains carbon, a biologically essential element, and appears to be actively delivering material to the surface through geologically disrupted regions. The surface produces oxygen through radiation-driven chemistry, although at a lower rate than previously estimated. Liquid water lakes may exist inside the ice shell itself, just a few kilometers below the surface. And the ice is not the dead, frozen barrier it was once imagined to be. It is dynamic, warm enough in places to recrystallize, and constantly being reshaped from below. Europa has water, it has carbon, it has a source of energy from tidal heating driven by its orbit around Jupiter. It may have oxygen seeping down into its ocean. There is evidence of sodium chloride, hydrogen peroxide, and carbon dioxide on the surface, along with hints of other essential elements. 3 basic ingredients for life water, the right chemical elements, and a source of heat appear to be present. But we do not know if there has been enough time for life to develop. We do not know the exact chemistry of the ocean at depth. We do not know how efficiently material cycles between the surface and the deep interior. We do not know whether the oxygen production rate measured by Juno is typical or whether it varies with plume eruptions, orbital position, and upstream magnetospheric conditions. And we do not yet know whether the shallow lakes proposed by Schmidt and her colleagues are common throughout the ice shell or confined to a few exceptional regions. Villanueva's team also looked for evidence of water vapor plumes erupting from the surface during their Webb observations. Researchers using Hubble had reported tentative detections of plumes in 2013, 2016, and 2017, but the Webb data showed no evidence of plume activity, allowing the team to set a strict upper limit on the rate of material potentially being ejected. They stressed that this non-detection does not rule out plumes. They may be variable, appearing only at certain times. All they could say with total confidence is that no plume was detected during those specific observations. And we do not know what lies at the bottom of those lakes hidden in the ice. Europa Clipper will not answer all of these questions. It is not a lander. It will not drill through the ice or directly sample the ocean, but it will map the surface in extraordinary detail, measure the thickness and structure of the ice shell, constrain the depth and composition of the ocean, and identify the most promising sites for future exploration. Some researchers believe the chaos terrains Tara Regio, Powys Regio, Thera Macula are the key. Land there, and you may be sampling material that has come directly from the ocean. Others argue we need to look at the non-chaotic regions, like Falga Regio and Argadnel Regio, to understand the broader distribution of materials and separate what is local from what is global. Future continuous telescope observations may even reveal temporal changes in CO2 distribution, showing us how quickly the surface chemistry shifts and whether supply from below is steady or episodic. What matters is that every discovery so far has pointed in the same direction, not toward certainty, not toward answers, but towards something that science values even more than answers: better questions. Beneath Europa's ice lies an ocean we have never touched, on a world we have never landed on, orbiting a planet so far away that light takes over half an hour to reach it. And yet, piece by piece, instrument by instrument, flyby by flyby, we are beginning to understand what is down there. Europa Clipper arrives in 2030. It will join ESA's Jupiter Icy Moons Explorer, which will make 2 flybys of Europa on its way to orbit Ganymede. Together, these missions will provide the most comprehensive look at Europa we have ever had. They will follow up on the oxygen measurements, the carbon detections, the plume searches, the chaos terrain analyses. They will carry forward every question the past decade of discovery has generated. And with that, we may finally learn whether we are alone in this solar system or whether, deep beneath the ice of a cracked and quiet moon, something has been waiting in the dark all along.